So in this video I want to look at another application of derivatives, and that is finding extremas. And it was one of the reasons for the development of derivatives and their first uses as calculus began to be worked out practically and applied in different things, because extremas are very important when you consider that a function or equation could model the relation of one thing being dependent upon another. If we want to find what is a maximum that we could do, or a minimum, or how to minimize cost, how to gain greatest efficiency in whatever we're modeling, extremas are often what we're seeking to find. And we can use derivatives for that, because if we think about what a derivative is, it's the slope of the tangent line on the curve. Well, an extrema is a point where the curve has been increasing or decreasing, and it comes to a point where it changes direction and starts the other way. But for an instantaneous moment, it's going to have a slope of 0 before it begins to turn the other direction, because you can't go from a positive slope to a negative slope without going through 0, assuming the curve is continuous. So that instantaneous point where the slope is 0 is our extrema. And we can use derivatives to find that point quite easily, because since the derivative is the slope of the tangent line, we'll just set that equal to 0 and solve for x. So in this example we have y equals x cubed minus 12x. So its derivative y prime is just 3x squared minus 12, using our power rule and our sum and difference rule. If we set that equal to 0 and solve for x, and this is a basic equation to solve. We can pull the 3 out. We get x squared minus 4 equals 0. And then factor the quadratic into x plus 2, x minus 2. And with our zero factor property, we know that x is equal to 2 and negative 2. So those are the two extremas on the curve. And we can plug that into the function and find the corresponding y value. So we would say y of 2, plug that in, it's 2 cubed minus 12 times 2, which is negative 16, and y of negative 2 is equal to negative 2 cubed minus negative 2 times, or negative 2 there, times 12, which is 16. So we found 2 points, the point 2, negative 16, and the point negative 2, positive 16. And those are these two extremas on the curve here. This lower one is obviously 2, negative 16. This upper point is negative 2, positive 16. So if you just have an unending interval from negative infinity to positive infinity, you're told to find extremas. You can say that the relative maxima is at the point negative 2, 16, because that's where it changes direction. It's going up, it's going up, it's going up, it changes and comes down. And likewise, the relative minima will be at the point 2, negative 16. Now, we may also have an instance when we're working with extremas on a given interval. So say that we're told to find the extremas on an interval from 0 to 4. Well, in that case, we'd need to say, is there an extrema, a relative min or max, on that interval? And on this curve, we know that there is a relative minima there at 2, negative 16. But you also have to include the endpoints, because endpoints could potentially be an absolute extrema. It could be the point that's farthest up or farthest down on a restricted interval. So you have to test those. So we can say that if we test 0, 2, and 4 on that interval, see what our mins and our maxes are, those will be the absolute extremas on the interval. So we can say that y of 0 will equal 0, y of 2 will equal negative 16, and y of 4 will be equal to positive 16. So on the interval from 0 to 4, we have our absolute max at the coordinate 4, 16, because that has the highest y value, and the corresponding min on that interval will be at 2, negative 16. So these are just two examples of how we can use derivatives for finding mins and maxes, either generally across the entire graph or finding an absolute min or max on a restricted interval. And they're both quite useful as you move ahead and start applying derivatives in different problems.